today we're going to start a new chapter, and it's actually the last chapter in a Calc 2 class or in BC Calculus in high school. So we're going to start out with showing a new way to find relationships between variables. So most of the time you've been working with y and x, two variables, a dependent variable and an independent variable. And to get some type of relationship, like y equals 2x, if you want to graph that, you can just plug values into the independent variable, like 1, and get the dependent variable 2, and you can plot them on a graph. Nothing wrong with that form of showing a representation between those two variables. But there is another mode that you can use, another form called parametric equations, or parametrics form. What you're going to do is instead of giving y as a function of x, you're going to give both x and y as a function of a third parameter. And it could be anything, but t is the most often used parameter. So you give x as a function of t, and y is a function of t. So for this particular graph up here, you could say x equals t and y equals 2t. So now the independent variable becomes t, and you have two dependent variables, x and y. And let's see if it works. Now you plug values into t. If I plug in t equals 0, I get 0, 0 for x and y. So I would, right there, that would be at t equals 0. And then when I go t equals 1, I get 1, 2. So this would be at t equals 1. At t equals negative 1, I get negative 1, negative 2. So that would be. So you might wonder, well, what's the advantage of this? Well, I can say the main advantage is, and the reason we use t as our parameter often, is that if we think of t as time, not only do we have this relationship, but we have some feeling of movement. We know that these points are here at different points in time. So for instance, if you went from this point here at t equals 1 to this point here at t equals 3, and if you think of t like in seconds, and say this coordinate system is in centimeters, you have some motion between time 1 and time 3. You've gone a certain distance in a certain amount of time. And I think you can find out what that distance is. If you use Pythagorean's theorem, you went from 2 to 6, so you have the square root of 4 squared, and the distance formula, or Pythagorean's theorem, the difference in the x values, so you have the square root of 20, or 2 times the square root of 5. So if the units are what I was saying, that particle would have been moving at that many centimeters per second during that time. And I think if you think ahead, if you were trying to get a rocket ship to go to some place in space, you're going to want to know something about the positions of the rocket ship at certain times. So another thing you could look at is what happens if you take dx dt. You get 1. And dy dt is 2. Well, what does dx dt mean? It means how much does x change versus a change in t. So that's saying as t changes by 1, x changes by 1. And as t changes by 1, y changes by 2. And since these are both positive, that means when dxt is positive, it must be moving to the right. And when dy dt is positive, it must be moving up. So we kind of know that it's moving up and to the right, even without looking at the different times. I mean, you can see it's moving up to the right because -1, 0, 1, 3, as time is getting bigger, x and y are both getting bigger. But we could have told that just from here. And this is a rather simple relationship. More complicated relationships parametrically, after you take the derivative, it might be at different times, it might be moving in different directions. So I'm hoping you can see some good things that could come out of that. Now, what else might you want to know is you might want to know the velocity when you don't have quite as simple of a relationship. We were able to find the velocity here because the distance, we could use the distance formula. But what if you had a relationship that looked more like this? So say you were at this point at t1, and you were at this point at time t2, and you wanted to know something about the velocity that you're going, you could say, well, I can't actually get the distance with the distance formula between there, but I can approximate it with this dotted line. So during this change in time from t1 to t2, I'm going to call that change in time delta t. During that time, there was a change in x and a change in y. So we could call this delta y and this delta x. Then, with the distance formula, we can say that distance is the square root of delta x squared plus delta y squared. So what did we do? We went that distance in this time. Well, it's not exactly that distance, but we could give an approximation for the speed to be the square root of delta x squared plus delta y squared divided by delta t, the distance divided by the time. And if you wanted to rewrite this, you could make delta t in a radical and call it delta t squared. Now we have speed to be approximately equal to the square root of delta x over delta t squared plus delta y over delta t squared. Now what happens is we bring this change in time smaller and smaller. What if we bring t2 closer to t1? As we do that, the amount that we're off using the straight line versus the curve gets smaller and smaller. So what we really want to do is make this change in time approach 0. So then the approximation is not an approximation, and it's an exact. And it will give us the speed right at that time t1. So what I have to do to get the exact is to take the limit as delta t approaches 0. Well, limits are always our friends. So if you have the limit of a function, you can make that the function of the limit. And we have the limit of delta x over delta t squared, but we can do that the limit of the first one times the limit of the second one. So I can just square this result and do the same thing over here. Of delta y over delta t. Now these things right inside these parentheses are something that should be recognizable. What do we have if we have a graph and we take the change in x over the change in t, and then you take the limit as delta t approaches 0? you get the slope right at that point. We get dx dt. This is the definition of derivatives that we've been using for a long time. So what we finally get is the square root of dx dt squared plus dy dt squared. And now we have an exact formula for the speed. Now, later on, I'll give you an example. But for right now, on this problem right here, could we do it? Yes, dx dt is 1, dy dt is 2. So the speed would be the square root of 2 squared plus 1 squared is the square root of 5. Well, that doesn't seem to go along with what we said before. The problem was, before I forgot to divide, that's the distance, I divided by the time. It was 2 seconds, so it really was going at just the square root of 5 centimeters per second. So my formula caught my mistake over here that I forgot. You don't just take the distance, because from this point to this point was 2 seconds. So anyway, now we have a way of doing it when it's not just a straight line. What else might you want to do in this new mode, this parametric mode? Well, maybe if you've got a curve, you'd want to know the slope of it. Well, whenever we're in the xy coordinate plane, which we still are, the slope is always the change in y over the change in x. So it's always going to be dy dx. Whether you're in rectangular or parametric, that's still going to be the slope of a curve. But we have x and y in terms of t. So what we're going to use is the second form of the chain rule that we learned. If we want to take dy dt, we can take dy with respect to any other variable times that same variable with respect to t. That was the second form of the chain rule that we used sometimes. So what do we want this time? We want an x here, because this is what we're trying to solve for, dy dx. So we get dy dx equals dy dt divided by dx dt. So now we have a way of getting slope. Now, a little bit more difficult, what if we wanted to go for concavity? Then we'd have to go to the second derivative, d squared y over dx squared. Now, we don't need really a new formula. We just know we have to take the derivative of this. But the thing that's sometimes hard to understand, you're still taking the derivative of this with respect to x. And when you do this up here, you're going to get this in terms of t. So what you have to do is call this new function up here, call it, say, big Y, and it's going to be given as a function of t. What you have to do is take now dy dt, so to take the derivative of that with respect to t, and x is the same old x. X hasn't changed, so you have to divide it by dx dt. That is a little complicated. That's how you get concavity from the second derivative. We'll give an example very shortly. Well, we've got a little bit of room here, so let's just pick a parametric equation. Let's let x equals a cosine of t and y equals a sine of t. Well, say we want to find and let's have a domain. A domain for our independent variable, let's let it go from 0 to 2 pi. And say during that path, we want to know how far we went on that path. Well, I don't have a formula for that. So what do I have to do? I have to think of a new formula. How can I get the distance that I went along a path? What have I got on this board that's going to help? I think the speed. The speed times the time is going to give the distance. So, but the speed is changing all the time. So we have to do this with an integral. So to get the distance, we go from time t equals a to t equals b and multiply the speed times the time. So the speed would be the square root of, this is what we just derived, dx dt squared plus dy dt squared dt. So we've got a new formula. It came out because we had this new problem. So what can I do in this case? I can take the integral from times 0 to 2 pi, the square root of, and what is dx dt? Dx dt is a times minus the sine of t. And dy dt is a times the cosine t. So when you square this, you get a squared cosine squared t plus a squared sine squared t. But if you factor out a squared times cosine squared plus sine squared, you're left with just the square root of a squared. And the square root of a squared is the absolute value of a. So when you take the antiderivative, that's just a constant. And then you get t from 0 to 2 pi. So you get 2 pi times the absolute value of whatever a is. Now I wonder if that makes any sense. Say we made a graph. What does this path look like? Well, when we start at t equals 0, we're at a cosine of 0. So x is equal to a, and y is a sine of 0. So you're at a 0. That's at time 0. Then at time pi over 2, you'd be at 0, a. And then at pi, you'd be at negative a, 0. And then at 3 pi over 2, you're at 0, negative a. And then at 2 pi, you're back where you started again. It looks a little bit like a circle. But could it possibly be a circle? Well, can we change parametric into rectangular? What could I do? I could go x squared plus y squared would be a squared cosine squared plus a squared sine squared of t. Well, cosine squared plus sine squared is 1. So what do we end up with is x squared plus y squared equals a squared. A circle with a radius a. So I hope you see that this is all kind of coming together. And you can see from dx dt, there's just so many things. I don't want to leave this before we look at them. What happens from 0 to 2 pi? The sign is positive, so as long as this is a is positive, you're going to have dx dt as be negative, which means you're moving to the left. So, and from 0 to pi over 2, the cosine is positive, so you'd be moving up. But then once you hit pi over 2, the cosine becomes negative, so you're moving down. So you can notice that the motion along this circle goes like that. Okay, so let's just look at a couple of examples. 1, we have a particle moving in the xy plane. According to this parametric equation, x equals t squared, I'm even going to rewrite it up there. X equals t squared, y equals t cubed. And we want to find a lot of things. First, the domain and range. Well, the domain is all the values of t that are possible. Well, there's nothing that prevents you from squaring or cubing t. There's not any like 1 over t or anything like that that would say you can't do it. So that would mean all t such that t belongs to the real numbers. T can be anything. So what's the range? Now you have to put the x values and the y values. Well, because x, you're taking t and squaring it, and you can use all values of t, you're only going to get 0 and above. So x has to be greater than or equal to 0, but y, since you're cubing it, could be anything. So y belongs to the real numbers. Now how does that help you? Before I've even sketched it, I know I can use all values of t. I know that I'm only going to have positive values of x, and I'm going to have y going over the whole number line. So we have some feeling what's happening. And we've got the domain and the range answered. Now, to sketch the movement, one thing you could do is plug in some values of t. So when t is 0, you get 0, 0. When t is -1, you get 1, -1. When t is 1, you get 1, 1. When t is 2, you get 4, 9. I'm sorry, 4, 8. So we have some idea what's happening. We started there at t equals -1, and this was at t2. So we have the feeling that the motion is kind of going up like this. Now, how could we kind of prove that? dx dt is 2t, and dy dt is 3t squared. So no matter what value of t you put in here, y is getting bigger as t is getting bigger. So it's moving up. So we know we're always moving up, whereas dx dt is 2t. So when t is negative, it's moving to the left. And that seems to be what's happening. When t is negative, it's moving to the left, and then it's moving up. So we have a feeling that our motion is like this. I think we have more than a feeling. I think we know that that's going to be the case. Okay, so what else do I want to find? I want to find a tangent line at the point 1, -1, right down here. So what do I need for a tangent line? A point and a slope. Well, I've already got the point. I need the slope. So what is dy dx? We proved that it was equal to dy dt over dx dt. And dy dt is 3t squared, and dx dt is 2t. So now we have an expression that gives the slope, but we have to plug in t. So we have to see, what time was it we were at 1, -1? And that was at time -1. If you're not sure about that, you can always go back and say x is t squared equals 1, and t cubed has to equal -1. Solve those simultaneously, and you get t must be -1. So if I plug that in here, I get the slope is 3/2 times -1, or -3/2. So my tangent line would be y plus 1 equals -3/2 times x minus 1. And does it make sense that you could have a slope of -3/2 at that point? And I think you see that it does. Okay, now where is the function concave up and concave down? Now we have to go to the second derivative. And like I was telling you, you now have dy dx. So this is like a new y. And it's a function of t, and it's 3/2 t. So to get d squared y over dx squared, what we have to do is to take the derivative of this big Y with respect to x. And we have to use this same formula. So we go dy dt divided by dx dt. Well, dx dt is still 2t, but now the derivative of this with respect to t is 3/2. So we get 3 over 4t. So what does that say for the concavity? When t is less than 0, you're concave down because this will be negative, and when t is greater than 0, you're concave up. So that means right here, we're going to go concave down in rising, and then concave up in rising. So I didn't do a very good job of that. It's concave down, and then that's concave up. What else do we want to find? The speed of the particle at 2 different times. Well, the speed is the square root of dx dt squared plus dy dt squared. So we have 2t for dx dt and 3t squared for dy dt. So the speed is going to be the square root of 4t squared plus 9t to the 4th. So at t equals 0, the speed is 0. And then at t equals 1, the speed is the square root of 13. Does that make any sense? Well, what does it mean for the speed to be 0? That it's not moving in the x direction or the y direction. And that happens only at the origin right here. So, what's the last thing we have to do? Find the length of the particle from this time to this time. So from this point to this point, what's the total length of that? Well, here we have to go the integral from one time to the other time. Well, we already said that's at time -1, and the other time is at time 2, and the speed is the square root of 4t squared plus 9t to the 4th dt. Well, we don't have a lot of room, and plus this isn't the idea of this lesson. It's actually an interesting integral to do without a calculator, but with a calculator comes out to be about 10.5. which makes some sense, because here, you're up here at 8, and here, so from here to here, from -1 to 8 is 9. So to say that distance is 10.5 does make some sense. Okay, let's do one more. I don't know why I called it 3. I guess it should be 2. Find the equation of the tangent line to this parametrically defined curve. Well, let's see. Let's this time get a sketch of it at the beginning. At time 0, you're going to be at 2, 0. So there's at time 0. At time pi over 2, you're at 0, 4. At time pi, you're at -2, 0. And at 3 pi over 2, you're at 0, -4. And then you're going to be back to where you started. So it looks a little bit like it could be an ellipse. And at 2 root 2, at the square root of 2 root 2, we want to find the equation of a tangent line. So, what do I need? A point and a slope. Well, I've already got the point, so to get the slope, I have to go dx dt is -2 cosine of t, and dy dt is -2 sine of t, and this is going to be 4 cosine of t. So that means the slope, dy dx, is going to be dy dt over dx dt. 4 cosine of t over -2 sine of t, which altogether is -2 times the cotangent of t. So to find what the slope is, we have to see at what time are you at this point right here. We know it's between time 0 and time pi over 2. So how could you find it? Set x, 2 cosine of t, set that equal to the square root of 2, and you could set 4 sine of t equal to the y value, which is 2 root 2. Well, you get what? That the cosine of t is the square root of 2 over 2, and the sine of t is the square root of 2 over 2. So that happens at t equals pi over 4. So now we know to put in pi over 4, and that's nice because the tangent and the cotangent of pi over 4 are just 1. So the slope turns out to be -2. So our tangent line is y minus the y value equals the slope times x minus the x value. So we were able to write the equation of that tangent line. Now, I also want to know whether there's vertical or horizontal tangents, and I want to know the concavity. So to get the concavity, d squared y over dx squared, we just did one similar, but this is going to be a little bit more difficult. Now we have to take the derivative of this with respect to t and divide it by dx dt again. So what's the derivative of this? I'm sorry, not this, but here's my new dy dx. So that becomes my new y. So what's the derivative of -2 cotangent of t? Well, all cofunctions have negative, so that means I'm going to get a positive 2. And the derivative of tangent is secant squared, so this is cosecant squared. So altogether you get negative 1 over sine cubed of t. So there's an expression that will give the concavity at any time t. So you know from 0 to pi, the sign is positive, which means the concavity is going to be negative. And look at it, it's concave down, and then from pi to 2 pi, the sign is negative, so the concavity is going to be positive. So, how about vertical and horizontal tangent lines? Well, if we write the slope to be negative 2, and the cotangent is the cosine over the sine, what's going to make that slope 0? If the cosine is 0. So it's going to be at pi over 2 and 3 pi over 2. And yes, there's pi over 2 and there's 3 pi over 2. And what makes a vertical tangent? When you divide by 0. That's at 0 and pi. And that's where we get vertical tangents. So, I think we really explored what parametric equations are like. We're still going to do some more with them in the next lecture. So, until then, take care.